Hello. Welcome to this joint event organized by the World Meeting for Women in Mathematics, which is taking place which is broadcasted. So the event will be also broadcasted worldwide. And we're organizing also together with the Conference of Probability and Mathematical Physics. And is it possible to see the program of the morning? Okay, so the program of this session is in fact a special session in honor of Olga Ladyzhenskaya. It's 100th birthday this year. And there will be two parts. One part is a film, which is made by Ekaterina Eremenko, who's with us today. Ekaterina, where are you? Okay, so you see Ekaterina, who's the film director. Please stand a little more. So that's for about half an hour. And then we have the second part, which is the more exciting part, which is the celebration for the OAL prize. So we still have to keep a secret for a few minutes. But then there will be the presentation of the prize. It will be recorded by Ingrid Daubechies. Then there will be a little film, which will be revealing the secret. And then some more comments by Ingrid. And then we'll have the Laudatio by our distinguished guests. And finally, the lecture by the prize winner. So enjoy.
Yeah, okay, so when the WM contacted us some time ago about this prize ceremony, asking us to organize it as a live part of their Zoom meeting, of course, we were extremely delighted about that. Because of the distinguished character of the name behind the prize, as we'll hear more about that. But also, the creation of this prize was one of the nice contributions which Stas and Andrei, Stas Smirnov and Andrei Okunko did for this year's ICM. So as in this conference, you have all of us have experienced that mathematical physics is really a very active field of mathematics at the moment, and it's great that we finally have a distinguished mathematics prize in mathematical physics. So we are really very happy about that. Maybe one more thing that this prize was sort of in danger because the ICM, as you know, was radically changed this year, but luckily it was saved by the Simons Foundation, which is also we should be thankful for that. So I hope you will enjoy this program, and let's start.
Один случайный знакомый, который кончал физфак, сказал: у нас есть такая Ладыженская, иди на физфак, не ошибешься.
Я у нее слушал курс лекций по дифференциальным уравнениям частных производных, по нелинейным. Это была виртуозность абсолютно. При этом она рассказывала часто свои оригинальные результаты.
Для нее самая привлекательная тема математики – это гидродинамика.
Have you heard of the Clay Foundation and their problems? One of the problems is a problem in fluid dynamics. That system of equations called the Navier-Stokes equations is still an open problem. In fact, Olga Ladyzhenskaya wrote a book on that problem.
Она была признана, такая советская Софья Ковалевская. И все это было абсолютно заслуженно.
Отец у меня был учителем математики. Это в возрасте 10 лет должна была проверять его, так сказать, своеобразный экзамен. Папа рассказывал мне элементы высшей математики, я должна была понять, правильно он рассуждает или нет.
Я занималась теорией вероятности всю жизнь, а она уравнение математической физики. И она попросила меня прочесть некий курс. Читать было интересно, действительно люди очень все остро понимали. И только Ольга Александровна иногда вдруг начинала не понимать. Это даже вызывало раздражение этих ее молодых людей, что как так, Ольга Александровна, что вы это? И они бросались на перебой объяснять. И только я один понимал, что она задает эти вопросы, либо в тех случаях, когда я по лености о чем-нибудь умалчивал, либо когда я начинал говорить о вещах, которые я сам плохо понимал.
Помню, вот я ее застал за писанием формул, заглянул через плечо, спросил, это что? Она сказала, вот, говорит, ищу многомерные странные аттракторы.
Ольга Александровна в свое время водила машину и с большим увлечением к этому относилась, но потом, недолго это продолжалось. Она говорит, а я, говорит, правила никогда не учила, потому что я считала, что у меня, говорит, логика достаточно сильная и хорошая, чтобы я могла разобраться в ситуации и знать, как себя вести на дороге. Вот так.
Оля сложная, но я стала придерживаться такой политики, что я все делаю так, как она хочет. Но она вообще за все бралась. На лыжах ходила. Она, между прочим, очень здорово съезжала с гор высоких. У нее всегда было другое мнение, чем тот, кто с ней разговаривал. Политические какие-то разговоры. И политические я старалась пресекать.
Знаменитое сочинение Солженицына «Красное колесо», состоящее из многих частей. И там есть некая героиня, которую зовут Ольга, профессор, такой гуманитарный профессор. Меня тогда очень поразило, что она чем-то мне напоминает Ольгу Александровну. Ну, а потом я узнал, что они были знакомы.
Звонит телефон, я снимаю трубку, звонит Солженицын. Ольга! Потом она мне объясняет, потому что куда денешься.
Ее сотрудники были вот просто за стенкой. Ее кабинет был здесь.
Это почерк Ольги Александровны. Одна из последних ее работ. Да. Верное и обратное неравенство.
It was very unexpected for me to know what here will be organized this excellent conference devoted to me.
For the beautiful and very moving film. That was really a pleasure.
Thank you. So now we are going to see the explanation of how the prize got created by Ingrid Daubechies, the former president of the IMU. And then we are going to see immediately after a little film announcing who is the prize winner. And then there will be again comments by Ingrid commenting why the choice is relevant. Okay, so let's go.
Pleasure that I accepted the invitation to introduce the Olga Alexandrovna Ladyzhenskaya medal. I was in the audience when Ladyzhenskaya gave the Noether Lecture in 1984 at the joint math meetings of the American Mathematical Societies. And the event still lives in my memory. Listening to her presentation and meeting her afterwards were full of meaning for me, who was just at the end of my own postdoc years, when I was still a young pipsqueak. There were then not many famous women mathematicians to look up to, and even fewer in mathematical physics, the field in which I grew up. The idea of offering this award at the 2022 ICM originated with the mathematicians on the ICM Local Organizing Committee. It seemed especially appropriate to honor this famous Russian mathematician in 2022, the 100th anniversary of her birth, and in St. Petersburg, the city where she obtained her PhD and started her career. With full approval of the IMU, other ICM local organizing committees in the past have awarded a prize at their ICM, honoring a mathematician or a milestone especially meaningful to the host city or host country. The Lilavati Prize in the 2010 ICM in Hyderabad is the most recent example of this type. Awarding the inaugural Ladyzhenskaya Medal during ICM 2022 was similarly approved by the IMU Executive Committee. Recent events put it out of the question to hold ICM 2022 as an in-person event in St. Petersburg. I'm glad that the inaugural awarding of the Ladyzhenskaya Medal is taking place during this joint session of the World Meeting of Women Mathematicians and the Probability and Mathematical Physics Conference, both satellite events of the virtual ICM 2022. In my view, the inauguration of the Olga Alexandrovna Ladyzhenskaya Medal Award offers hope to all mathematicians. Our community reaches across national boundaries, and it is good to recognize that kinship. I would also like to reassure everyone in the audience who may be concerned by this issue that none of the funding for the award comes from Russian government sources. Olga Alexandrovna Ladyzhenskaya played an important role in the partial differential equations development of mathematical physics, and her work has had an extraordinary influence, inspiring many other developments in mathematical physics and beyond. It's therefore especially fitting that the Ladyzhenskaya Medal is an award in mathematical physics, intended to be awarded every 4 years to recognize revolutionary results in or with application to mathematical physics. There's no restriction of age or gender associated with the prize. In particular, it can be awarded to men as well as women. My introduction has taken up enough time. I'm sure everybody is curious to learn who was selected by the 2022 Ladyzhenskaya Medal Committee, chaired by Giovanni Felder from ETH Zurich. So let's see who they picked.
I have traveled quite a distance from where I began. I grew up in Kharkiv in Ukraine. It's a city whose spirit and resilience makes me tremendously proud, especially in these times. I had a clear passion for Russian literature, especially poetry. But in the former Soviet Union at the time, humanities fields were too interwoven with ideology for me. Mathematics is not political, so I chose it instead. I was very motivated to try to get admitted to Moscow State University, but it was notorious for discriminating against Jewish applicants. I studied math really hard to get in, by a miracle I did. And afterward, I felt I had to justify my being there, to study for all my Jewish friends who were denied the opportunities that I had received. And in doing so, I fell in love with math for life. My parents were both accomplished mathematicians. My father, Yakov Jitomirsky, and especially my mother, Valentina Barok. My mom was the only female full professor of math in the entire Ukraine. She was very much in the orbit of Olga Ladyzhenskaya and knew her quite well. Ladyzhenskaya was a really great mathematician. She was the very top person in partial differential equations in the entire Soviet Union. My mom, of all people, would say things like, math is not a good job for a girl. It conflicts with family obligations that were expected of a woman at the time. She felt that for a woman to make it as a mathematician, she had to be fully dedicated, like Ladyzhenskaya. My mom did manage to balance both, but it was hard. I arrived at UC Irvine right after finishing my PhD in Moscow in the early 90s. My husband Vladimir and I only came to the United States because he was offered a postdoc in Southern California. At first, I worked as a part-time lecturer at UC Irvine because it was all that was available. I like directing my graduate students. I try to lead them to where I have a sense they would feel the most mathematical beauty lies. For me, that beauty has always been most evident in the small denominator issues that pop up in various questions. And there are some areas where my taking a different approach has produced solutions. I study the world of quantum mechanics. It's governed by the Schrödinger equation and based on the notion of an operator. The state of a quantum particle is something impossible to observe. What you can actually see in some way is the action of an operator. My main contributions have been in models of quantum physics, but related difficulties are well known also in the classical setting. If you look purely at the motion of the moon around the Earth, we can solve this problem, They move in elliptic orbit. But there are many more forces acting in these two bodies. The periods of some orbits are too close to each other, and then small denominators can prevent the stability of the solutions. So you need a way to deal with them. I solved the first piece of the puzzle of how to treat the small denominators in the mid-90s. It was for the almost massive operator arising from a model of an electron in a crystal subject to a magnetic field. So there is a natural period associated with a crystal, and electron in the magnetic field also has periodic motion. And if you put a two-dimensional crystal in a perpendicular magnetic field, there is a collision of these two periods. It was realized that there are several small denominator problems embedded here, leading in particular to the metal-insulator transition. In metal, electricity flows freely, so electrons move all over. In an insulator, electricity isn't conducted and electrons stay confined. I discovered the sharp arithmetic phase transition between the confined and intermediate phase, where electrons may move freely, then stay confined, then move again. It wasn't even predicted in physics, because the timescales of this behavior are longer than the lifetime of the universe. So it's a purely mathematical construct. It just so happened that my best results are on this model. By far, I am not the only member of my family who went into math. In fact, Vladimir and I have raised even more mathematicians in our family. My daughter Oля is a professor of math at the University of Waterloo. My other daughter Yelena is a graduate student in math at UC Berkeley. And my son Andrei is an undergraduate at Stanford, also planning to major in mathematics. My family helps me remember that math is not the most important thing in life. And I'd be fine even if I fail in all my research attempts. Somehow, it's helped me to keep going and keep trying. I'm glad that, like my mom, I've been able to blend a career in math with family life. I may not have followed her advice, but I followed her example. Hopefully, there is poetry in that as well.
Whoa, whoa, what a wonderful way to start the list of Ladyzhenskaya medal winners. Congratulations to you, Svetlana. 2022 will really stand out in recognition for your achievements. A plenary talk at ICM 2022, and now being awarded the first Ladyzhenskaya medal. On a more regional note, it's also the year in which you were elected to the National Academy of Sciences in the USA, the country where you now reside and work. This is quite a year for you. As I described earlier, this award can be, and I'm sure in the future will be, given to male as well as female mathematicians. Accordingly, the selection committee surely did not restrict itself to considering only women. I'm so very happy that it so happens that the first of these medals is given to a woman. Just like it was a wonderful coincidence that the first awarding of a Fields Medal to a woman happened when the president of the IMU was a woman. This is a wonderful additional reason for celebration at this world meeting of women mathematicians. Not only are we witnessing the inauguration of a new prize named for a wonderful woman mathematician, but we can now also rejoice in its first awardee being a woman. In light of recent events, it's also quite a coincidence. And indeed, the selection committee had finalized its choice of the awardee already in January, well before Russia started the present war with Ukraine on February 24. It's quite a coincidence that the first awardee of this new prize, named for a famous Russian mathematician, is herself from Ukraine. She was born in Kharkiv and grew up there. Even in dark times, it is some consolation that we can continue to recognize our kinship as mathematicians. Congratulations again, Svetlana, even if only remotely. I look forward to seeing you in person again soon and give you a big hug then. In the meantime, let me just lift a glass to you in celebration.
You, please. Congratulations.
Supposed to say something now or later?
I think you have a lot of chance to say something later. So, congratulations, Svetlana. And now. Okay. So the next in the program is the Laudatio for the prize, and this is going to be given by Artur Avila. Please, Artur. From IMPA and Zurich.
So thanks, congratulations, Svetlana, and it's a pleasure to be here and have the opportunity to see this beautiful video of the life of Ladyzhenskaya, and most important in this particular case, to be able to tell a little bit about the work of Svetlana and just to get one idea of some of the great things that she did, for which are in part for why she was selected for this prize. It's going to be just a little impression, so that it will be people can get. She will give a longer presentation about some more recent aspects of her work. So I will just mention some things that are maybe a little bit older, but maybe new for some of you. Which is related to, she has worked on many different things, and I don't want to give an impression that it's more restricted than it is, but I want to concentrate on let us say, what I believe is a big passion of her. So among all things that she has worked on, she loves particularly working and finding everything that she can about the so-called almost mature operator. And from this, it goes to other things, but she really spent a huge part of her time since the beginning trying to discover what there is about this operator. So I talk about this. I met her for the first time in 2004. I was going to make some, was trying to find some pictures and so on, even asked her, but then I realized that there would be this video which had enough of this kind of thing, so it's unnecessary. But when I met her, she had already given a big contribution, and what did I know it for was, so let's see, so I was starting to try to understand her work on an almost mature operator. So what is it? So as she mentioned in her video, it's an operator. It's going to be related to some quantum mechanical model. But if you just want to know the formula of the operator, it's quite simple. So it's a one-dimensional model. So let's call it H. It will be acting, let's hope that doesn't make too much, on L2 of Z. So that's the operator. So there is a lattice, just one-dimensional. And what's the formula? So it acts on sequence. So they ask to draw it. So H acts on a sequence U, and the nth element, it just interacts. There's a near neighbor interaction plus a diagonal term that has the following form. Let me write it already in this form. There's a cosine, and there are many parameters here. So that's the formula. So you see that there is some sort of a discrete Laplacian, and then there is the diagonal term has this cosine form. It's quite. It is motivated for being coming from a specific model. It is also within a more general family of operators which have a similar form of this. So you could play with this term here. It's still staying in this one-dimensional setting. So the thing is that this operator, it depends on those parameters, and we are interested, especially in the case where alpha is, the interesting case is when alpha is irrational, and this term here is important, but we have less role in this talk. And this term here is quite important. So this is the coupling constant, and it will determine if the behavior will kind of, so we can imagine that if the coupling constant is small, then this term here dominates, and you are going to have a behavior that could be hoped to be close to if you didn't have lambda. And if lambda is larger, you could divide by lambda, and then this term would be very small, and you could imagine that you could have something almost given by like a diagonal operator. So this would be just a very small initial approximation of this, but it's known in similar models if you didn't have this particular form, but you replace it here by something maybe with a less regular dependence, for instance, something that was legitimately an independent choice of, so this is called the potential. So the potential would be given by some would be independent on the sides and not very kind of well correlated as it is. Then it's well known that in this one-dimensional case, you always have this behavior that predominates. In other words, you are going to have this operator, you have just point spectrum with, yes, so let me talk about this first theorem then. So let me give you some general information. So first, things are not very simple. So there's a simple formula. There's going to be, so first thing that you want to have these self-adjoint operators, look at the spectrum, for instance. So let's call the spectrum is some sigma that depends on all those parameters. And it's not a simple object, it turns out. So it's not just an interval. The things that comes from this, from particular this irrational frequency is going to create some complicated structures that then can, in particular, she has analyzed a lot. But let me say that this, for instance, it tends to be a fractal set. It's compact. And okay, I'm not like it goes out of order, but it's kind of interesting information. It's going to be a Cantor set, so that's it is in fact a Cantor set, and it should come later because it's actually one of her theorems. But it's so early in the theory that to say something interesting about this is okay. So that's one theorem that she has proved. So, so you have this. There are more information of this. It's a fractal set, but it's not like a dust. It often has positive measure as well. So there is a lot of interesting things. So how you can put your hands on this is something interesting, but then above that, if you're interested on really understanding the operator and actually the dynamics, so this is going to code the dynamics of some part. Once you introduce it in the Schrödinger evolution, so at some point you're going to do things like this. And then when you consider the semi-group, you're going to need to understand what about the operator, not the spectrum precisely, but about the spectral measures of this operator. And the key characteristics that may happen is that, so you're interested in the spectral measures. And then the thing is that when possible behaviors that are interests that they can be classified by Lebesgue's decomposition. So it could be, they are supported on this kind of fractal set. So there is this big thing. It could consist of just eigenvalues. So maybe this operator would have a base of eigenvectors. This is a possibility. So you could have a possibility. This would be the atomic part of the spectrum measures might exist. It can have, and then there could be a continuous part that is natural to split into a singular continuous part and absolute continuous part. So that's just in principle. And it was, there is one more information that comes here is that there is some mysterious, so for this particular operator, so that, so what happens that since it was particularly important in physics, there was a lot of, including physicists or computing things, and they were getting very much further in advancing the theory, sometimes without complete, like they were finding things that later could be justified, but they found many rigorous things. And one of them about this was that there was a duality for this operator that's called Aubry duality. In this equation that comes from consideration of some Fourier transform, which so cosine has two modes, exponential, so has two Fourier modes. So basically, under Fourier transform, it sends these two Fourier modes becomes this discrete Laplacian. Discrete Laplacian becomes a cosine, but it inverts the role of the size of the contributions here. So the kind of exchange. So duality of Aubry shows that there is some relation between coupling constants lambda and lambda minus 1. And to have this exact formula, that's why there is a 2 here. So, but this duality was kind of in an intuitive level, was since they explained in the paper that was analyzed, this would relate those two things. So in a sense, what was expected to be dual of the atomic part would be the absolute continuous part. So the pure point spectrum would be related to absolute continuous spectrum under this change, and expected something also in the other direction. And this would remain a little bit mysterious under this. So in a sense, this operator has to have lots of structure. It might, if it has at all this part, it should also have this other part, maybe for other values of parameters. So there will be some complicated relation between this and the study of the dependence on parameters might be something of interest. Then it was, there is one important characteristic as well that for this operator, that is the Lyapunov exponent that allows to consider, so let's maybe right here. So where does it appear? It appears when you consider this as you try to find generalize the eigenfunctions for this operator. So you try to solve equation like this. This becomes a simple discrete difference equation of second order. And then you can write it in a matrix form. So you have a relation that is un plus 1 un is going to be given by some matrix here that I call an, has a very easy formula, not an times un minus 1. And then if you want to try to understand what happens, how to relate the two sides here with two sides far apart, you have to start multiplying matrices like this, ak plus 1 to some point. So this would relate things that are n minus k apart in here. So you have to consider these products of matrices. Those matrices, they are in SL2R. In this case, I don't write the formula, but so it's just a matrix of determinant 1. So the products will still have determinant 1. So the characteristic of this will be what's called the Lyapunov exponent. It's that encodes the average rate of growth of this. So you try to look at this. So it's a multiplicative product. And then you expect that if you look at the size, it should be in average at least. So let's divide by, let's put it by n minus k. And then this would be, it should converge to the Lyapunov exponent. So let's put in the other direction. So it should go to, or it should be about it. Let's say that the Lyapunov exponent is a quantity that should govern this in average. There can be exceptions, and the exceptions are important, but just from the point of view of the tendency of how the matrices are growing, you can capture it in this Lyapunov exponent. And the matrix growing means that you can have exponentially, let us say, it means that the solutions can decay exponentially as well. Like to get something decaying, you need to apply a big matrix as well. So a positive Lyapunov exponent enables the potential of having solutions that decay exponentially. And if you're so lucky that they decay exponentially on both sides, then you're going to have an L2 solution. So one source of so-called localized eigenfunctions, which are those that exponentially decay on both sides, is by this dynamical behavior that depends on this Lyapunov exponent. And then, let me say, but then it turns out that what is the Lyapunov exponent? Then it's possible to explore this relation, that's how it was done at the time, to get the answer here. So there is the so-called, so I think this is the Aubry-André formula, I hope it not. So that it turns out that the Lyapunov exponent has a relation, can be computed, and this is again a magic. So this is related to dynamical systems. The questions that we get to ask about the almost mature operator are not reasonable to be asked in general, but here they are. So it is that the Lyapunov exponent has a formula. You're not supposed to have formulas for those kind of things, but here there are. So the Lyapunov exponent is just a log of, so it's just log lambda. So it's max of log lambda and 0. So it has to be, so it has determinant 1, so it's at least 0, the Lyapunov exponent, but as long as lambda is bigger than 1, it's going to be actually a positive, and it will be dual to situation where it is 0. And that is another theorem that's like the validity of the formula. So this was found out by the physicists, and then, but to show that it actually holds always under no conditions that was put here, that's kind of I call it the Bourgain-Jitomirskaya formula. And let me say that this, but why I'm kind of ahead all the time, but because now I can explain about what the theorem that she would like me to start first. Is, well, now you see that there is a transition now there. So lambda equals 1 is important because it's the auto-dual parameter. It's also clearly where something is changing from the point of view of the Lyapunov exponent. And then now you have to try to see what's the consequence of this in this picture here. And then there is the theorem that she's very proud of, and justifiably, because it kind of sparked the whole development in this field, as I would say. So, but then her theorem, let's say, so for lambda bigger than 1, almost surely, so there are many parameters, so I won't give as much precision as I should like, but it's easier to state. Then localization holds for almost every choice of parameters. And for lambda less than 1, you have the spectrum is almost surely absolute continuous. Right. And so this fact, lambda is supposed to be positive here, so otherwise I'd have to put some absolute value somewhere. So that's what they call the metal-insulator transition. So that it is relevant from you really understand something important about the quantum motion that's supposed to be coded by this by models given by this operator. Because so what it means is that here you have absolute continuous spectrum that's like that if you didn't have this at all. And this means that actually the wave particle moves like it's the wave, the quantum probability, it kind of moves, it kind of gets quite spread and has a momentum that grows, and that this can be understood in several levels. I'm not going to, so that's related to ballistic transport and things like this. So things kind of move fast, they become spread and away very fast. While here, so this is this part, so this would be the metallic part, and in this part here, the thing doesn't spread at all. So the dynamics is like quasi-periodic for that. So the thing basically stays at the same place. So this happens here. And then it is transition between this metal part and this one that's called the insulator part. This gives the title of her article. And what is so that's great from the point of just from the physical point of view. But what about the impact of this theorem mathematically as well? So the impact was first that the proof of this is that original attacks on classes of operators like this used some kind of perturbative techniques. So the idea was, for instance, to take lambda extremely large, right? And then to apply some method that would kind of show that the introduction of this part here would be just a perturbation of a diagonal term, and you could try to analyze, for instance, using a KAM iterative scheme to show that actually you are governed by the diagonal term remains after perturbation. But this is only applicable in some kind of perturbative regime, and this is kind of a non-perturbative theorem that really gives you the actual full picture. And how she managed to do this, she changed it, she realized that it was necessary to change focus and concentrate exactly on this constant. So she works with for instance, that's the main part that she was working on. This is then done by duality. It was to look at the impact of a positive Lyapunov exponent on the solution. So she was understanding very well how the solutions behave. And she still keeps trying to understand even better how the solutions behave. But she was able to find this decay of the eigenfunction on one side and match with a decay of eigenfunction on the other side. So it's a beautiful, beautiful theorem. But on top of arriving there, she revealed that we should focus on that. This had immediate impact, particularly on attracting people, and Bourgain was very influenced by this. He said, so he then wrote many articles on that, he collaborated with many people, wrote a book, and then he clearly said himself that what changed the field was exactly this paper and the introduction of the focus on the Lyapunov exponent. I told the story a little bit out of order because Bourgain was attracted by this theorem, but you see already his name here. Actually, they proved this theorem sometime later. It's a consequence of a more general and very deep result that it was in turn one of the things that attracted me to work on this, because I come from a dynamics perspective, and then I was really impressed by what they did with this Lyapunov exponent. Let me tell what's this theorem. It is, what's behind this is that the Bourgain-Jitomirskaya theorem is the continuity of the Lyapunov exponent. So what basically they say, it works in a more general thing. So they show that the Lyapunov exponent can define it depends on several parameters here and depend on the energy. And maybe I could play also with this, and for once I make this become a general analytic function. And then given all this, if you change all parameters, what you can prove, what they prove, is that continuity of the Lyapunov exponent with respect to parameters for real analytic. So you can replace a cosine by a real analytic function. And now, so this is a deep theorem in analysis. I don't think herself realized it was so deep, but coming from dynamics was immediately clear that this was a big deal. And let me say how delicate it is. It is it's a continuous at irrational frequencies, at irrational alpha. It's actually, you might think that the rational case, it's easier, it should be easier. It is in fact easy to analyze, and it's easy to see that it's not continuous when you consider rational frequencies. So that, in a sense, it's a very hard analysis technique to show that actually, as the frequencies become more and more irrational, then the kind of oscillations that you find get smaller and smaller. And it's also kind of very delicate with respect to the potential. You cannot weaken substantially real analytic. If you can get finite differentiability, you start finding discontinuities, as was shown later by other people. that's really something. And from this theorem, it was what used to justify the formula that the physicists had found. I need to finish soon. I'd like to just add one more thing. Another theorem that she proved that was quite important was early on, was the extension of this non-perturbative analysis of absolute continuous spectrum. She did another paper with Jean Bourgain that showed that this situation that spectrum tends to be absolute continuous for small coupling holds for other real analytic functions here. And the significance of this theorem from, is in part that if you have, this theorem is valid even with a alpha which is extremely, so you see that the rationals are kind of strange and are making things complicated, but this holds even when the rationals are not that good. So there are no exceptions for this. You just need the coupling to be controlled. And from the perspective of dynamical systems, it's very strange because you have this oscillating behavior that I just mentioned, because there is this discontinuity of Lyapunov exponents that's connected to some complication of the dynamics. And usually this complication of dynamics should produce some post-Lyapunov exponents as well, and then leads to some localization. And they found out, and also I believe it was not realized that immediately at the time, how strange it was that it doesn't. Just they managed to find a proof that established that Lyapunov exponent, and hence there was absolute continuous spectrum, but the Lyapunov exponent was zero, independent of all those oscillations that are happening. And then it took a long time to really try to understand a little bit better of how this can be compatible. But they just proved it in another beautiful paper. That's just the beginning of the story. After this happened, many people got attracted to the field because of the beautiful theorems, and then there was influence. There's a whole school that worked on that Xu works with, and so on. So the influence on the community of those works, but a big part of this is also by her own work. So she keeps working on this until now, and then I hope to see very soon what she has now to say about her latest work. So that was just presentation of her old work. Okay.
Be nice to take questions even for you, but let's rather proceed with the program because we are sort of tight in time. So Svetlana, please. Svetlana is going to give her ICM talk now, and maybe you can tell the title yourself because I don't have it here.
Okay, so may I say a few words first before the ICM talk and before my time starts? Right, so because there is exactly 55 minutes for the ICM talk, I don't want to use any of that for other things. So I'd like to thank everyone involved with this prize. It's really overwhelming for me, and I'd like to thank people who created this prize, who conceived it, especially Stas, who is here, and Andrei Okounkov, and also the Simons Foundation that rescued it. And I'm also very grateful to WM Square and to Antti and the organizers of this meeting for this opportunity to celebrate in person. And I'm definitely extremely grateful to people who nominated me and to the committee that selected me, and also to Ingrid and Artur for their wonderful presentations, and to the audience for being here so patiently. And I understand that it's a problem because I'm scheduled to speak tomorrow also, and you may be in horror now that you will have to listen two of my talks after. Also, Artur already gave a part of it, sort of. But there is good news. Tomorrow's talk is fake. So I'm only talking once. It's now. So this will be the ICM talk. On the other hand, since it's the ICM talk, it will have to be, I will have to repeat some of the things that I would otherwise not say because Artur already said them and so forth. I'll have to ignore that. And finally, going back to the prize, I still want to say a few more words before the talk. Of course, I think I was destined to receive this prize because, you know, how many, everybody in the audience, think of when have you heard the name of Ladyzhenskaya first? You probably were in grad school, or if you're Russian, you may have been in undergrad. But I have heard it literally from before I was born, because my mom, as you've seen in the movie, she was a mathematician, actually very much in Ladyzhenskaya's orbit. Ladyzhenskaya was an opponent and at my mom's both candidate and doctoral dissertations. So opponent sounds as is a bad word, but actually opponent is kind of a supporter. That's the opposite. So it's a person, a senior person who comes to your defense and gives a talk about your work and stuff like that. So, and I definitely heard Ladyzhenskaya's name said around me, and always with utmost respect. And I know that my parents, both of them, thought the world of her. I heard things later when I started to understand things that since the mid-70s she was the top PDE person in the entire Soviet Union. And I heard a lot of that growing up. Unfortunately, I never met Ladyzhenskaya, although I had plenty of opportunities for that. And in fact, I did meet her as a baby, but I don't remember this. But my mom would quite often, like maybe once a year or 2 years, travel to St. Petersburg to meet Ladyzhenskaya and to speak at her seminar. And she would quite often take me along, but she would normally drop me off at one of the St. Petersburg museums and go meet Ladyzhenskaya. So I never had a chance to actually see her. So I guess I will move to the talk. And again, please don't start the time yet. So once again, it's an ICM talk, so I will have to be very inclusive towards algebraists and such people who are not probabilists or mathematical physicists, so it's definitely not a talk I would have given in this audience, so please be patient. And I guess we can start.
Thanks and congratulations once more. And of course, on behalf of our conference, thank you for Marie-Françoise and all the WM people of giving us the opportunity to have this session here. And thanks Artur, of course, for the beautiful Laudatio. And maybe Marie-Françoise wants to say something still.
No, I have not much to add, just to say that this is the closing of this OAL celebration. We are very happy that it was done together with the PMP meeting so that we can be here live with a group of people involved in this mathematical topic. And for us also the end of our WM Square meeting, which we hope to be live in the future. Okay, so many thanks for doing that together with us. Thank you.